Hi everybody, my name is Tanishka and today we are going to be learning about one of the most common financial instruments called bonds. In this video, we are going to learn a lot of things, starting with the basics such as the definition, the different types of bond that are available in the market, some basic terminologies, and then we'll move on to some computational things such as learning what an accumulation function is, present value, time value, as well as yield. And these will really help us to understand how to calculate bond prices, bond yield, and slightly more advanced stuff such as bond duration. So, what are bonds? A bond is a fixed income financial instrument that represents a loan made by an investor to a issuer. In other words, a bond is a written contract between the borrower and the lender. Usually, the government or corporations are the ones issuing bonds when they need capital. Like any other loan, a bond pays interest periodically and repays the principal at a stated time as per the agreement at the time the bond was issued. There are many different kinds of bonds in the market, such as coupon-paying bonds. These bonds usually pay periodic interest or coupons to the bondholder, usually semi-annually or annually. Next, we have zero coupon bonds. And as the name suggests, these bonds do not pay any coupons. We also have perpetual bonds. These bonds have no maturity date, meaning that they pay coupons forever unless they are called. We have other bonds such as convertible bonds and callable bonds. In this video, we are going to focus mainly on coupon-paying bonds. There are certain words or terminologies that come up very often when you're dealing with bonds. Firstly, we have the face value, also known as notional. This is the amount of money the bondholder lends to the issuer and is also the amount used to compute the periodic interest payments. This is usually denoted F. Next, we have the redemption or maturity value. This is the amount that is to be repaid at the end of the loan period. This is usually denoted R, and most of the times, the redemption value is the same as the notional. Next, we have the redemption or maturity date. This is the date by when the issuer fully repays the principal to the bondholder. Next, we have the coupon rate. This is the bond's interest payments as a percentage of the notional, and it is to be paid to the investor at regular intervals during the term of the loan. This is usually denoted as C%. Alongside this, we have M, which denotes the number of coupon payments per year, and N, which is the total number of coupon payments made. Let's see the terminologies in action. Let's say you have a coupon-paying bond with a face value of F and a coupon rate of C%. In that case, your cash flow would look something like this. At t equals to 1, you would have your very first coupon payment of C% times F. At t equals to 2, once again you would have a coupon payment of C% times F, and this would continue all the way until t equals to n minus 1. At t equals to n, which is also the maturity date, you would have your coupon payment C% times F plus your notional, which is F. Now let's take an example with real numbers instead of working with just alphabets. So let's say you have a 3-year coupon paying bond with a face value of $100, coupon rate of 2%, and a yield of 7%. In this case, your cash flow would take the following form. At t equals to 1, you would get your very first coupon payment, which would be 2% of 100, $2. At t equals to 2, once again you would get $2 as your coupon payment. And at t equals to 3, which is also your maturity date, you would get the coupon payment plus the face value. So 2 plus 100. Now that we understand the terminologies and we also know how the cash flow look like for a coupon-paying bond, the question is, how do we calculate the price of a any-year bond given that we know the face value, the coupon rate, and the yield? For that, we first need to understand how to calculate the accumulation function, the present value, and time value of a given cash flow. Let's take a look at these in the following slides. The accumulation function is a measure of how good an investment is. It is the ratio between the value of an investment at time t and the value of the same investment at time 0. Here are a list of some common accumulation functions based on the different ways interest rates are compounded. Firstly, we have simple interest rate. In this case, the accumulation function is simply 1 plus t multiplied by r. Next, we have compound interest rate. In this case, the accumulation function is 1 plus r to the power of t. Next, we have nominal interest rate that is compounded t times annually. In this case, the accumulation function is 1 plus r divided by p and the whole thing to the power of p times t. Over here, p is the number of times the interest rate is compounded annually. Next, we have effective annual interest rate, in which case the accumulation function is 1 plus the effective interest rate to the power of t. And finally, we have continuous compounding, where the accumulation function is simply e raised to the power of t multiplied by r. Let's take a look at an example to solidify our understanding on accumulation function. An investor makes a deposit today to earn an effective interest rate of 4% over the first 3 years and a nominal rate of 3% compounded monthly for the next 2 years. What is the nominal continuously compounded interest rate over the subsequent 5 years in order for the original investment to be tripled by the end of 10 years? So here, the question states that the original investment, which would be V0, is tripled by the end of 10 years, which is V10. From the previous slide, you would know that V10 over V0 is the accumulation function, A10. And this equals to 3 because it is tripled. Now let's read the first half of the question to craft the accumulation function. We know that the deposit earns an effective interest rate of 4% for the first 3 years. For this, the accumulation function would be 1 plus the effective interest rate to the power of the number of years. Next, it earns nominal rate of 3% compounded monthly for the next 2 years. That would be 1 plus 3% divided by 12 to the power of 2 times 12. Here, P is 12 because it's compounded monthly. And finally, for the last 5 years, it is being compounded continuously. And for that, the accumulation function is e to the power of 5 times r%. And the question wants you to find the value of this r, which should be very easy because we know that e to the power of 5r equals to 3 divided by 1 plus 4% to the power of 3 multiplied by 1 plus 3% over 12 to the power of 24. And if we do the math, we will know that r eventually equals to 18.42%. The present value is the current worth of a future sum of money or stream of cash flows, given a specific rate of return or discount rate. For example, for the given cash flow, the present value of the cash flow would equal to the summation of each individual stream of cash flow divided by its respective accumulation function. Time value is the direct opposite of the present value. Time value is the future worth of a sum of money or stream of cash flow, given a specific rate of return or discount rate. In this case, the time value at time t equals to the present value multiplied by the accumulation function, which is also the summation of each individual cash flow multiplied by its respective accumulation function to the power of the number of time periods left to time t. Note that discount rate equals to 1 over the accumulation function. Given this cash flow, the following equation with variable r is known as the equation of value. Any non-negative solution of r to the equation of value is called the yield, or eternal rate of return. One should think of the IRR of C as the amount that the prevailing effective interest rate needs to be in order for one to be indifferent between the cash flow C and $0. Now that we understand how to calculate accumulation function, present value, time value, as well as yield, we can proceed to calculating bond prices. To calculate a price of a bond, all you have to do is compute the present value of all the payoffs you receive during the term of the bond. Let's take a help of an example to understand how to calculate bond prices better. Suppose a 10-year bond with a face value of $100 pays semi-annual coupons at a nominal rate of 8.4%. From this sentence, we know that the maturity date of the bond is 10, and the value of each coupon payment is 8.4% of $100 divided by 2, because it is a semi-annual coupon. Let's move on. Given that the bond yield is 10% convertible semi-annually, what is the price of the bond when it is issued? So we know that the bond yield is 10% and it's convertible 2 times per year. So the accumulation function for that would look something like this. 1 plus 10% divided by 2 and the whole thing to the power of 2t, which is the same as 1.05 raised to the power of 2t. To visualize the payoffs of this bond better, let's illustrate this in a cash flow diagram. So here, at time t equals to 0, you receive nothing. At time t equals to 0.5, which is your 6 months mark, you receive your very first coupon payment of 4.2. At t equals to 1, you once again receive your coupon payment, and this continues all the way until t equals to 9.5. At t equals to 10, which is your maturity date, not only do you get your coupon payment, but you also get back the face value. So altogether, you get $104.20 back. As mentioned earlier, the price of a bond equals to the present value of the cash flows, which equals to the summation of the present value of each payoff. So in this case, for the very first payment, the accumulation function would be 1.05 raised to the power of 2 times 0.5. And that would be the present value of the very first coupon payment. Next, for the next 4.2, the present value would be 4.2 divided by 1.05 raised to the power of 2 times 1. And you keep doing this until your very last payment, for which the accumulation function would be 1.05 raised to the power of 2 times 10. And once you compute this entire equation, the value would be 90.03, which is the price of the bond. For any time t in the lifetime of a bond, the nominal yield of the bond is the nominal internal rate of return compounded m times per annum. In the previous slide, we calculated the price of the bond based on the present value of its payoffs. That method can be generalized into the following formula, where PT is the price of the bond at time t, R is the redemption value, F is the face value, C is the coupon rate, and lambda t is the bond yield at time t. If you recall from earlier slides, I mentioned that the redemption value is usually equal to face value. If that is the case, then the formula can further be simplified into the following form. A bond is said to be priced at a premium if the price of the bond is greater than the face value, and this occurs if and only if the coupon rate is greater than the yield. A bond is said to be priced at par if the price equals to the face value, which happens if and only if the coupon rate equals to the yield. And finally, a bond is said to be priced at a discount if the price of the bond is less than the face value. And this happens if and only if the coupon rate is less than the yield. Now, if you look closely at the very first equation that I provided on the slides, you'll notice that the lambda, or the yield, is always in the denominator of the equation, which means that as your yield increases, price decreases. And when your yield decreases, your price of the bond increases. That is to say that the price of the bond is a decreasing function of the nominal yield. Here is a graph representing the relationship between the price and yield of a bond. Note that the maximum possible bond price is attained when the yield is zero, in which case the stream of cash flow is undiscounted. That is, the bond price is simply the sum of all coupon payments and the redemption value without any discount factor. In the previous slide, we learned that the price of a bond is inversely related to its yield, but we want to be able to quantify this sensitive relation. We want to know by how much would the price change given that the yield changes by a certain amount. This is where the concept of duration comes in. Macaulay duration is the sensitivity of the bond price with respect to the changes in yield. Macaulay duration is defined as the partial derivative of the price of a bond with respect to its yield. We can also represent it using the following formula. Since different bonds have different prices, it becomes harder to compare the sensitivity of bonds against each other. So in the industry, people usually calculate and report the modified duration instead of the Macaulay duration. Modified duration ensures that the sensitivity of the bonds are on the same scale for easier comparison between them. The modified duration is given by the following formula. Note that the modified duration formula has a negative sign in front. Since price is inversely related to yield, the partial derivative of price with respect to yield will always be negative. Hence, the negative sign ensures that we always report a positive value for the modified duration. As mentioned, the Macaulay duration is the partial derivative of the price of a bond with respect to its yield, which means that the slope of a tangent line of a price-yield curve is represented by the Macaulay duration. And since the modified duration equals to 1 over p multiplied by the partial derivative, we can quantify the slope of the tangent line using the following formula. This also means that the following formula is true. The change in price can be defined as the multiplication of the negative of the modified duration with the price and the change in yield. Now let's take a look at a question to solidify our learning on bond duration. A 25-year bond pays coupons semi-annually at 6% and has a 9% nominal yield convertible semi-annually. The face value of the bond is $100. Given that the modified duration of the bond is 10.618, estimate the change in price if the yield increases by 1 basis point. So we know that the change in price can be represented by the following formula. It is approximately the multiplication of the negative of the modified duration with the price of the bond and the change in yield. We know that the modified duration is 10.618 and the change in yield is 0.0001 from the question. However, we do not know the price of the bond, so let's calculate the price. We know that the bond matures in 25 years and each coupon payment is $3 and the accumulation function is 1.045 raised to the power of 2t. Here, we divide the coupon rate by 2 because the question states that it's a semi-annual coupon. And the value for p for the accumulation function is 2 because the question says that the nominal yield is convertible semi-annually. From here, we can draw the cash flow diagram and calculate the present value of the payoffs to find the price of the bond. Great, so now we have all the information that we need. We simply have to plug the values into our formula to get the change in price, given the change in yield.